Dr. Michael Overcash is the CEO of Environmental Genome Initiative. And currently he's the CEO of this initiative. Before, he was a professor at the North Carolina State University from 1971 to 2007. And he's an expert in life cycle inventory, sustainability, has written books on several of these topics. And then it's a pleasure for us to have you to give your lecture in this webinar. Please add whatever else you want to add about you. And thank you for giving this webinar.
That's plenty. And so it's what I'm going to talk about today is this concept of chemical substitution, but in a variety of different ways. And so I want to kind of introduce what we're going to talk about, which is there's a variety of motives for doing chemical substitution, which we're going to talk about. Then there's a sort of a historical context with which chemical substitution is in a variety or is in an arsenal of other alternatives for improving manufacturing processes. And then we'll talk about some examples that we go through that. So we have added to chemical substitution this idea of the broader environmental analysis and the broader environmental changes. And we'll see what that expansion does in terms of areas of discussion. So when we look at the industrial basis for chemical substitution, we find that there are several different goals which are occurring. One, of course, is the one that's just been mentioned by Dr. Raisa, which is trying to find chemicals that have a lower environmental impact. And the impact can be in a variety of different metrics, whether it's the properties, whether it's on a regulated list, whether it has impact on stratospheric ozone, et cetera. So those are metrics, if you would, that we're trying to lower. Not always all at the same time. However, when you look at in industry, there are other motivations for doing substitution. One is that we're often trying to find chemicals which improve the efficiency of the process. And examples would be better lubricants, more effective solvents, et cetera. And those are very much attached to the specific process. The third motivation is an interesting one, which people have now connected the idea of adding chemicals, using different chemicals, which extend the life of the product that's being made. And I've given you some illustrations right here. And you can see the life of the product can be 10 to 30 times longer. And hence we have not an obvious environmental benefit, but a product benefit. However, when we look at it in terms of life cycle analysis, that extended life based upon the product where it's used is really has a very large and defining impact. So with those in background, I think environment is just one of several major reasons that we look at chemical substitution. Now, the basic concept here, of course, is chemical A is going to replace chemical B. And the first factor that we need to examine is the most critical. And bottom line, the chemical A has to work exactly or better than chemical B in the particular application where it's being applied. So this is a very engineering-based requirement. And interestingly enough, it's not necessary that chemical A, substituting for chemical B, be a lower cost. That can often be in higher cost because it's the impact in the product where there are additional benefits which compensate for costs of chemicals that are being substituted. So as I mentioned, this is generally very much related to the application in which the substitution is being examined. The additional factor which has emerged is the basic question: is this substitution better for the environment, or does it have unintended adverse consequences? This is what we're going to include in this broader environmental changes. The ability to make this analysis typically depends upon life cycle tools. And so we're building a bigger and bigger collection and effectiveness of these tools. So some of the origins of the chemical substitution by the environment. If we look, and this is very much a United States timeline, what happened is this began in sometime in the mid-70s, where the 3M Corporation instituted a program called the 3Ps, Pollution Prevention Pays. It turns out that what it was is a incentive program for the employees of 3M to come up with new and better ideas that would reduce pollution and be compensated financially for that. And so they actually had this same program under the umbrella of safety and under the umbrella of manufacturing efficiency. And so they simply extended it to this idea that can we find improvements from our employees thinking about the problem that would reduce pollution itself. So then that in the early 80s, North Carolina, which is where I'm located, began or set waste minimization as the top priority for hazardous waste management. So in our country, hazardous waste regulation began in the early 80s. It was this period in the early 80s when we developed what's called the Pollution Prevention Roadmap. You'll see that in just a minute, but it's an interesting concept because until the roadmap occurred, that is, what do you have to do? You could basically look at 50 or 100 pollution prevention things which had been written up and not be able to do the 101st one. What do you do? And so we unified what had been done and created this roadmap for pollution prevention. By the mid 80s, the Fortune 5,000, Fortune 1000 corporations all had cleaner production technology programs. So a major shift in the period of 5 to 10 years. What really drove it in the United States was in 1986, the federal government passed a law called the Community Right to Know Act. And without going into the detail, it simply said that corporations had to report their emissions to the environment, and the community had a right to see that. And so out of that became something which in this country, each state had what are the top 10 polluters, top 20 polluters, and no corporation wanted to be on that list. And so they had to do something, to act. And so they had several choices. One, they could have gone to more waste treatment, simply put in more control, or they thought about it a little bit and realized that they could also do a lot in the area of prevention. And so the pollution prevention programs grew out of this, if you would, adverse public relations that comes from being listed as the top polluter. And so that really drove the circumstances in this country. And so at the same time, in the mid 80s, this concept that was developing in the previous 5 years here was started in Europe under the banner of cleaner technology. And so it began and grew along the same sort of lines which I've shown here. So that as you can see, tells us that this idea of looking for change to prevent pollution has a substantial history to it. And so the hierarchy, if you would, that came out of this is shown here. And it's at the top, this idea of waste minimization that was added to the middle, which is waste treatment, if you would. And that is added to the idea that if you don't treat it, it ends up somewhere in the environment. And so that top block became the focus. People simply ask, what are you doing to prevent waste? Whether it's process modification, recycle and reuse, it didn't matter. You were at the top of the hierarchy. And that was the goal for examining how to make improvements. So as that all began, people sort of digressed in terms of what do we call this? So in this country, pollution prevention, cleaner technology in a lot of the European countries. Now we see green chemistry, etc. These are essentially all synonyms of the same thing. And so if you do a literature search, you put in all these different terms and find sort of a large category, a large listing of alternatives. So chemical substitution, as I mentioned, is one of the things which was examined in this whole field of cleaner technology. But what do we mean by the broader impact? And what we have connected, if you would, here, and Carpentier was one of the first people to publish this, is that we're actually dealing in industrial manufacturing with 5 different scales of phenomena. At the left-hand side, the nanoscale, that's where the molecules are reacting or they're being heated or a variety of things which are taking place at a molecular level, catalysts, etc. Those activities are occurring, however, in systems which have physical space, liquids, gases, solid media, etc. This micro scale is where molecular processes are actually translated into change. Mesoscale is just simply the physical units, if you would, that contain the process units. We have reactors, heat exchangers, distillation columns. All these are operating at the mesoscale. So right now you can see molecular processes are affecting physical phenomena, are then affecting the behavior of the unit processes. At the macro scale, we put the unit processes together into a production unit line, if you would, or process description. And then those occur in individual plants. At the macro scale, not only do we have one plant, we have plants in a supply chain. So a single plant rarely operates in isolation. You have to begin in nature, taking materials out of the ground, building molecules eventually to get the supply chain of the product itself. All of those individual plants located all over the world, if you would, are then affecting the megascale, which is the environment. And so the environmental genome, which we'll talk about in just a minute, allows us to actually describe all 5 of these scales and the actual dependency of each scale on the other. So now for the first time, we can quantify the entire system, not just as a single answer, but as the individual pieces which are occurring within that system. I mentioned the process. Here's just an example of a process flow diagram. You can see reactors, heat exchangers, etc. So those occur in every one of these plants. This is the physical description of what those plants look like. And so those are where the chemical substitutions begin to have their effects in this process. So let's take a minute and look at the environmental genome. What is it? The website is given here in the top, but it really is the quantification of manufacturing of the 100,000 what are called chemicals in commerce. So in REACH and in our US system, 100,000 chemicals produced at 1 metric ton per year or higher are in a list. And those are what drive the manufacturing of all the products in the world. And there are trillions of products, but they're all made with the same 100,000 chemicals. And so the environmental genome is targeting the providing information on the 100,000 chemicals so that people can then do analyses on trillions and trillions of products, whatever they want. Now, these products turn out to be what we of human beings have created. So the environmental genome, we say, is mapping the essential building blocks of human creativity, what it is in the products that we make. So this catalog gives us environmental emissions. We are currently looking at the four major areas of manufacturing, if you would, or impact in our society, which is manufacturing itself, transportation, the energy grid, and agricultural production. So what we now know, of course, is that if there are environmental pollutants, there will be exposure, and hence the link between what we're doing in the process. The characteristics of the environmental genome are, first of all, very high granularity, lots of definition about processes. There's data files then on the chemicals that are currently in the environmental genome, which are not 100,000, believe me. We're not there yet, but it's related to the Sustainable Materials Management Analytic Framework, which in the EU, in the IPPC, are the kinds of areas where this information is a direct value. So chemical substitution then, and I want you to, this is a main concept, if you would, requires two things. One, the assessment rather of the chemical substitution. First of all, we need to know the environmental metrics per kilogram of chemical A and chemical B. But then we need to know how many kilograms of those chemicals goes into each unit product. So this is the use of the chemicals. And these two are balanced together. You can have a high environmental impact, but a low kilogram per unit product. And that is the combined effect. So we're going to look first at example one, if you would. And it's a substitution of a phosphorus-based flame retardant for a halogen-based flame retardant in computer printed circuit boards. So obviously the motivation you can see is the one that Raisa and has talked about earlier, which is we're trying to eliminate brominated, chlorinated, other halogenated materials, looking for substitution. And so the question is this going to be a net environmental benefit, or might it be one that has unintended consequences? So first of all, we have to begin with the environmental metric, the environmental profile, if you would, per kilogram of product. So the brominated one, the halogenated one, which I mentioned, TBPBA, is tetrabromobisphenol A. The chemical structure is on the left-hand side of the screen here. And on the right, we're showing the chemicals that come all the way from the oil in the ground, if you would, shown on the right, building the molecules, and then eventually the TBPA. Obviously, we have to get bromine from the earth. Turns out it's mostly in places like the Dead Sea and in underground liquid deposits in the United States and elsewhere. And we need natural gas for some of the processes itself. So this is what's called a chemical tree. And I'll show you another example of this shortly, but this is the one for the brominated compound. For the phosphorus-based compound then, we have a similar concept, if you would. On the right-hand side are the materials in the earth, ranging from crude oil to coal, which we need for the metallurgical coke, and then phosphorus in the ground. The brominated compound has got a name which is like 5 words long. I won't give it to you, but the chemical structure for DOPO is shown on the left-hand side. So that's the flame retardant that's being compared to this flame retardant. In the application, again, is computer or printed circuit board, which is a universal sort of application. So the first step then, and I'm going to use energy as the environmental metric because it's easy to kind of get your understanding of it. For the TBPA, if we look across the entire supply chain, we can see that we use different kinds of energy. We use a relatively modest amount of electricity. A lot of it are the things that we use in manufacturing for heating, steam, diatherm. Sometimes we have very high temperature processes, which is furnaces. And then we transport chemicals from one plant to the other as we build this on a global scale. And we also have introduced the idea of energy recovery. We know that in these processes, if there are high temperatures, then there are the potential to recover that energy and use it elsewhere in the plant. And that's what we include in energy recovery, giving us a total of natural resource energy. So natural resource energy, in simple terms, is the energy of all the fuels, all the material extracted from the earth to build the individual molecules, in this case, the brominated and the phosphorus-based materials. And so here you can see when you add these up, they're basically the same. In fact, I need to, in all honesty, tell you that in the life cycle characterizations, if things are within 20%, maybe even 30%, they're effectively the same because the amount of variability in these analyses is pretty significant. It's not like picking up a chemical and analyzing it on a mass spec. And so these are effectively the same. So in terms of the environmental metric per kilogram of material, we have effectively comparable materials. But if you look at the functional unit, which I mentioned is the printed circuit board, we have, it turns out, two scales of printed circuit boards. We have large ones, which go into servers, go into high-end PC boards, large computers, mainframe computers, etc. And then we have smaller ones, which end up in your cell phone or your laptop. And what we have found is that the existence of the flame retardant in the printed circuit board, so this is in the physical structure of the board, adversely affects the transmission of electrons within the system, if you would. And so we have to add the right amount of flame retardant for each type of material. And what we found is that the for small circuit boards, cell phones, laptops, it doesn't make any difference. The two flame retardants can be used interchangeably. We get the effective circuit board performance that we want, and therefore either one could be substituted. And so the answer is you can go from the halogenated to the phosphorus-based one, and have this improvement. However, for the large ones, the answer is not so easy. The phosphorus-based flame retardant has a larger effect on the circuit board performance, such that you have to add more circuit board, if you would, or more circuit board to accomplish the same task. And so the phosphorus-based flame retardant requires, in kilograms per product, which is now the circuit board, is larger. And so the analysis, which you see here on the left-hand side, we can see on the basis of the circuit board itself, that the the bromine-based flame retardant needs about 11,000 megajoules of natural resource energy, which is about 700 kilograms of CO2 carbon footprint. But the phosphorus-based one is more like 16,000 and 950 kilograms of CO2. So now you can see that what was essentially an equality of the environmental metric per kilogram of flame retardant, in this case, is been taken over by the application in the product, such that the phosphorus-based flame retardant is simply not better for the environment. It's counterintuitive. And so what this points out is one very important factor is if you don't quantify the entire system, you really can't predict what is going to be the better or the worse for the environment. And so here the chemical substitution turned out to be worse for the environment and therefore not justified based upon environmental considerations. Second example is another chemical substitution in which we're going to look at carpet. And you may or may not know, you look at the top of the carpet, that's what you and I walk on and can feel. But underneath it, there's a backing, thing that holds it to the floor, keeps it structurally stable, allows it to be flat, if you would. And for that, there are two alternatives that we examined. One is PVC, polyvinyl chloride, and the other is styrene butadiene latex. So the idea is, can we substitute styrene butadiene latex backing for the halogenated polyvinyl chloride backing in this commercial carpet? And so we'll use energy and carbon footprint to look at these alternatives. So here I've shown in yellow the results using the same energy profile, which I showed you earlier, of the polyvinyl chloride. It turns out there's got two pieces in the carpet. One is the PVC itself, and then the other is the plasticizer, the phthalate, which makes it, if you would, flexible and allows it to perform as a carpet. So we have to look at the chemical tree, the supply chain of both of these chemicals to get the total for the polyvinyl PVC backing of the carpet. And we can see here it's about 73,000 megajoules per kilogram of product, per 1,000 kilogram of the PVC. At the bottom in green is the styrene butadiene latex backing. And here we can see that, again, the same energy parameters, it's about 25,000 megajoules per 1,000 kilogram of SBL, styrene butadiene latex. So on a metric of environmental metric, in this case, energy per kilogram of chemical substituted, which is styrene butadiene latex, it appears to be significantly better. Let's look at the CO2, the carbon footprint. Again, at the top is the PVC. It's about 4,500 kilograms of CO2 per metric ton. And the styrene butadiene latex, about 1,700. So again, both energy and carbon footprint, two environmental metrics, are giving us similar direction in terms of the potential benefit of these chemical A, which is styrene butadiene copolymer. Now let's look at the carpet itself. So this is the second element, which is how much of this material is needed per square yard. SY is square yard of carpet. And here we can see, again, the difference between the two is been sustained, but is not quite as large. Remember, before it was a factor of 2 or 3 maybe. Now it's much smaller, and so as a result, we can look at the answer is still the same. Chemical A, styrene butadiene latex, substituted for PVC, is a better environmental choice. However, in context, we can realize that what we're doing is affecting one part of a product, in this case, carpet. And so you might ask yourself, well, what is the energy to make the entire carpet per square yard? Well, it's 160. So it's significantly larger. So we're affecting something which is 5 or 10%, if you would, of the overall carpet. And so, but it is the step in the right direction. And so when we look at chemical substitution, I think the thing we need to recognize is that it's not necessarily going to change the entire, in a significant way, the entire product. It is going to change it in part. And therefore, that's our goal, is step by step to be making changes or improvements which lead to environmental benefits. Okay, so there's two examples, again, chemical A for chemical B that are being substituted. Next, we're going to look at another comparison, and this is of a variety of crop protection chemicals, which I've shown here. So we have 8 separate chemicals. As you can see, from their molecular formula shown here. They're complex chemicals. So it's not going to surprise you that there's a lot of information that needs to be collected within the supply chain to be able to build these molecules. So the question is, which of these might we pick? Which chemical might we pick for crop protection, which has the lower environmental benefit, or sorry, the higher environmental benefit, the lower environmental impact? So this is the supply chain of the smallest of these chemicals, chloropicrin. And so when we use the supply chain here, there are several things that are useful information by looking at it in this sort of Excel style format. First of all, the salmon colored cells, the ones on the right, those are the natural resources in the earth. And so when the environmental genome creates these profiles, you automatically start getting information value. In this case, if you add those up, it takes about 5,750 kilograms of natural resources to make 1,000 kilograms of chloropicrin. So again, an immediate concept of the efficiency, if you would, of the process of making this particular chemical. But then if you look within the supply chain here, for example, look at nitromethane here in the middle. If you add up the nitric acid, oxygen, and propane, those numbers are the masses, if you would. You find out it's much bigger than 395. Basic principle, when chemicals go into a process for manufacturing, what goes in is always a lot larger than the products which come out. It's just the nature of the conversion, the chemical reactions, if you would. And you ask, where does that difference go? Those are the wastes. Those are the environmental emissions. So immediately we can get some notion, if you would, not necessarily of the characteristic of the emissions, but we get a notion of scale of emissions by looking at a chart like this. And of course, obviously, on the left-hand side is the 1,000 kilograms, the metric ton of chloropicrin. So we have to repeat this for all 8 of these chemical agricultural crop protection materials. And so let's start to look at it. Here we've listed the chemicals on the left-hand side. We can see the energy requirement, natural resource energy, megajoules per kilogram of chemical. And what you'll notice here is that many of them cluster, in sort of the 100 to 200 range. Some of them are quite a bit higher. Dinotefuran, 523. So the amount of energy, if you would, and consequence impact is variable, with some very high and some pretty much in the middle. If we look at the CO2 from the supply chain, again, so this is from materials in the earth all the way to each of these chemicals that you see here. Again, we see a modest range, again, some very high, many of them sort of in the 5 to 10 range in terms of kilograms of CO2 per kilogram of the agricultural chemical. So that's the environmental metric that we talked about, that we're trying to acquire for these individual chemicals that are being potentially substituted. The system that we're looking at, of course, is a hectare of agricultural land growing, corn, rice, you name it. And so for that, we have the amount of the crop protection chemical needed per hectare of land. And it varies substantially, as you can see, from 0.066 to 390. This number, this application rate, is the effectiveness. Low numbers mean it's very effective at controlling agricultural pests and other concerns in the production of these crops. And 390 is very high. So what we did then is to take this field application rate multiply it times the CO2 per kilogram of the chemical to get the next to the last column on the right, which is putting the environmental metric CO2 per hectare of agricultural land. And we can see again, and so this column is oriented from the smallest to the largest. And we can see indeed, there's a very substantial range. Now, what we're trying to, what I want to point out though, is that these higher numbers, the one at the bottom, turns out that if you look over the left-hand side, their environmental metric per kilogram, they're not that big. You know, they're pretty much in the same range as the others, but it's this effectiveness factor in the application to land, which is the driving force. It has the higher impact. And so again, chemical substitution can depend, if you would, both on the environmental metric, the things on the left-hand side, or it can depend on the application. The last column I just put there to help you understand how large the life cycle analysis is for each of these chemicals. These are the number of blocks in that diagram that I showed. This is the small one. These are the numbers that go into the rest of them. And some of them, as you can see, are 200 and 300, 500, 600 for dinotropyron that we had to produce and put together to create this chemical profile, if the environmental profile. So again, what this points out for you is that acquiring the environmental information per kilogram of the chemical can be a very large task and requiring lots of information. And so it's typical only for systems like the environmental genome, which are doing this routinely, to be able to acquire this. Now, what the interesting thing is that even though there are lots of chemicals in there, many of those are ones which we use over and over again. And so you don't have to recreate them every time you do an analysis. They're simply there to be used. You have to assemble them. And so you can see down at the bottom there, chloropicrin, which is has some of the lowest effectiveness, only required 17 gate to gates. So again, another example of substituting chemical A for chemical B, and again, the impact of the use in the product. The fourth example, my last example, is chemicals A and B. In this case, the chemicals are plasticizer used in vinyl flooring. When you look around your house or in the airport or wherever, you'll see vinyl flooring. And so we're going to be looking at the chemical A. The chemicals we want to potentially consider are diisoheptyl phthalate, DIHP, and diethylhexyl adipate, DEHA. And those we're going to look at whether or not those can be substituted for DEHP, diethylhexyl phthalate, which turns out that it has a significant environmental impact in areas that we haven't yet sort of examined. So the first thing that you should ask is, well, are these substituted one for one? Well, if you look at the second column, second row rather, SF. SF is essentially the ratio of the, in this case, DIHP needed per kilogram of DEHP. And so it's slightly lower. But they're effectively about the same. So now we're talking about something which might be very similar in terms of mass substitution in the product, not the differences, for example, that we saw in the printed circuit board. So here is the chemical tree for DEHP, the chemical that we're trying to, if you would, eliminate and substitute with other chemicals. Again, the same salmon-colored cells. In this case, about 1,600 kilograms of natural resources are needed to make 1,000 kilograms of DEHP. And again, the same concept, mass flows going in being higher than those going out. And so this is DEHP. The DIHP, the diisoheptyl, is here. It's slightly lower, 1,350 kilograms per 1,000 kilogram of material. So again, slightly lower in terms of natural resource impact. So those salmon colored cells, even though I've talked about energy impact, I've talked about CO2, there's another one, which is the consumption of natural resources. And those are the salmon colored cells. So automatically the environmental genome is giving us another environmental metric, which is how much material are we taking from the earth to create the individual chemicals that we're interested in substituting. So now we have put together the chemicals, the DEHP, and which we're trying to eliminate, and the two other chemicals. We put them in 100 square meters of vinyl fluorine. And so we can see at the bottom is CO2. And indeed, the DIHP and DEHA are a little bit better, but look at the scale. They're like 20 or 30% better, maybe even 10%. So not a huge impact, but necessarily, fortunately, a better impact than DEHP. But if we look up at the top and we look at the disability adjusted life years, what's called a daily, and don't ask me to explain that right now because it's that's another lecture altogether. But it is essentially a metric used to look at human impact. In this case, the human impact of vinyl fluorine is the loss of chemicals vaporizing, if you would, or volatilizing from the vinyl fluorine, so that they affect the people who are living in the house or walking through the airport, etc. Plus also all the supply chain, all the chemical plants, all that's added together here. And so if you look at the daily graph at the top, immediately recognize it's in logarithmic scale. So down at the bottom in CO2, what was 10 or 20% difference, up here, it's 100 to 200 fold difference. Huge differences in the daily or the human toxicity parameter. So again, here we can say, even though the chemicals are used at about the same level in the product, again, about the same, the impact in environmental metric per kilogram is huge. And therefore signaling that the benefit of substituting DIHP, diisoheptyl phthalate, for DEHP provides a significant benefit for chemical substitution. So in conclusion, what I'll try to look at this in terms of some important points. Chemical substitution, I've used that term quite a bit. There's also a community which uses it as called alternative assessment. And that's a community which is looking at alternative assessments, changing from one thing to another, not necessarily chemical A to chemical B, but looking at that. That is a large community, which is, and that's a major area in this whole effort to improve manufacturing. So again, bottom line, we're trying to make chemicals better. We're trying to make chemical use in products better, and therefore we're trying to make products better. The broader environmental analysis that we're performing here, again, in all four of the illustrations that I've shown you, have these two metrics: environmental impact per kilogram of chemical and kilogram of chemical per unit of product. And so we need to always put those two together. In the studies that we've done, because of the high transparency in the environmental genome, we are able to actually look at what are called the hidden environmental benefits. And that's because we now can look at individual process manufacturing, not just at one plant, but at an entire supply chains to look for potential benefits. And so the environmental genome is continuing to sort of expand our environmental understanding of new chemical uses. And so I think to summarize overall, you'll get a better understanding of the fact that in some cases, chemical substitution, A for B, can be good when you look at it from an environmental metric point of view, but when you look at it from a product point of view, it may not be better. And we need to differentiate between those two, because one of them is a benefit and one of them is an adverse impact of a chemical substitution. And as Dr. Rice has said, we need to avoid the latter one and try to focus on the environmental benefit. So Dr. Ghani, I'll stop there and we will address questions.
Thank you very much, Dr. Overcash. It was a very, very interesting lecture. And I do hope there will be questions. I can see already that Dr. Razia has a question. She has raised her hand. Please unmute her and let her ask the question.
Thank you very much, Dr. Overcash. That was a very informative lecture, and I learned many things. I was wondering one thing. When you calculate the environmental impact, I do not see you considering water footprint or solid waste production. I would like to know whether we can ignore them, or are they less important in terms of, carbon dioxide production or others, if I compare. And also, yeah, that's my first question. Did I ask the other question too? Because I have.
Yes, go ahead. Yeah.
Okay. So when I think about life cycle and analysis, sometimes I'm like, what do you call it? I get at loss. For example, sometimes we use raw materials which may not be environmental friendly. And if we even do the analysis of the raw material, what are the impacts of those raw materials we are using for a particular product? Should we include that also in the life cycle analysis of a particular product? The impact of the raw materials they're using, because we could have alternative raw materials for a specific product. So these are two questions.
Very good.
For
okay.
now.
Yes, okay, we can ask more. So let's talk about the life cycle one first. In the life cycle, we start with materials in the earth. So everything that comes out of the earth that you've mentioned, ores, fossil fuels, etc., they all have an environmental impact at that point in time. And therefore, we have to include that in the analysis that we're doing. So we do try to include that, but I have to admit, it is limited by the amount of information that one may have on a particular site or location. Your question, though, about water and solid waste, etc., in the essence of simplicity, in this lecture, I've just used two, which is an air emission and an energy requirement. There are about 15 different environmental metrics which come out of the environmental genome analysis, and water happens to be one of them. Solid waste is another one. Human toxicity, we saw in that one analysis for the vinyl flooring. So when you do the life cycle analysis with these sort of current or the next generation tools, the kind of things that we're doing, you get all of those things at one time. It's just that the life cycle impact assessment, which turns the life cycle inventory into those parameters which you described, all have to be done separately. So by all means, they are there.
Thank you very much. If I have any more questions, I'll come back again.
Okay.
Okay, there is a question on the chat from Dr. Yasir Arafat. Let me read it for you. Did you consider inherently safer design concept for product design stage during the lifecycle based analysis?
Very good. I'll have to say that the audience for the information that we are collecting turns out to be not just, it turns out the most important audience are the people who design products. And right now they're operating in an environment where, well, we don't know what the environmental impact is. So we're just going to design the product. We're going to do it because it looks cool. It's different. It's got great colors. It does all the things that go into design, which is a very dynamic field. What they've been able to do is to be able to just simply do it. Now we're putting on the table, well, here are the environmental footprints of all those things which you're selecting to put into the design. And when you do that, that allows them to be, if you would, more informed so that when they're looking at how you want to design this, are there alternatives? They can pick the alternative that has the lower environmental impact. And so they're not doing this because they're intentionally producing products which are not good for the environment. They're doing it because they don't have the information to make better products. And therefore, we feel strongly that that's a very important automation. Thank you for the question.
Okay, any other questions? I have a number of questions, but I will just stick to one or two now.
Okay.
In the examples that you showed, you already started with candidates that could be used as substitution. Were you given those candidates, or did you first do a survey to find those candidates?
I would have to say that we are, in most cases, asked, is chemical A better than chemical B?
Okay.
And it is the people asking the question, I think, who have the challenge of figuring out what are the alternatives. Because from a life cycle point of view, we have no idea whether it works in a product or not.
Yes.
It's only that knowledge base, which is way outside our field, that tells us what might be alternatives. But it is very important to generate those exactly as you described.
Okay. I think there is a related question in chat also. How do we quickly get the information on possible chemical alternatives? Probably similar question.
Yeah, that's outside my field. I'm a chemical engineer, you know, and the product side of this, the product designer side of this, those are the individuals who have all the creativity for all the great products that we're making to try to decide, well, are there choices? It's pretty unusual that there are not choices. It's just that if they're just doing the basis on what's cool or what looks nice or what's efficient, they're not including the environment.
Okay, there is somebody who's asking, can I also ask one question? Yes, please. Either show your hand.
Yeah.
Then we can unmute you.
Yeah, hopefully everybody can hear me. So my name is Renate Becker-Arnold. I'm working in BASF in Germany in a chemical company. And I'm together with Seda, one member of the scientific advisory board at OPCW. So thank you very much, Michael, for that very interesting presentation. So what I often experience is when we speak about green chemistry, it's really only the substitution and looking on hazardous properties and somehow to get rid of really hazardous chemicals. And I think what you brought is really a step into the right direction to look it from a broader view. So what I'm always asking myself is a little bit how do we take into consideration social economical aspects as well. So if there is really a big benefit from a hazardous substance used in a production cycle, and it's the products, the end products are beneficial for society. So and we can handle those hazardous chemicals due to a proper risk assessment. I always ask myself, what then, or why then doing substitution? And this is something, it's more common, but I would really like to know what's your thought about that.
I totally agree. I often tell the people we work with, which are, and again, BASF has been a real leader in this whole field, is that if you're, and these are discovery chemists, is that if you are finding a cure for cancer, I don't care how you make it, let's do it, okay? That's an extreme example, but it points out the fact that the application of what you're doing does have a substantial impact on what we're prepared to manage in terms of our environment. So people are doing economic and social life cycle. That's not what we're doing. Our environmental genome database is probably now over 2,000 CAS chemicals. So it's certainly one of the largest individual databases. It's only focused on the environment. These other factors have to be brought in, and they are routinely. And I think, as you saw from one of the examples, it can override the environmental footprint, particularly cost. I mean, often when we put in chemical substitution, chemicals which are more expensive and they make processes more efficient, we're actually saving substantial amounts of money.
Okay, thank you very much for your comment here.
Okay, there is another question in chat from Zulfan. He's asking, in your examples, you're using cradle to gate approach. Is there a reason for not going further, like using cradle to cradle approach?
Yes, because the decision on chemical substitution often depends upon the, if you would, the chemical itself. So its supply chain. How a given chemical is used in the variety of different potential uses is substantial. And so we tend to stop at that point, although when we do more complete analyses of chemicals or products, we do add the use and the end of life phases. The end of life phases are now getting very interesting because we're now looking at greater and greater emphasis on recycling end of life products. And so now we're bringing chemicals back from, let's say, plastics, for example, back into the supply chain, which then reduces the amount of cradle to gate information for making virgin products. And that's all embedded in the kind of analyses that we're doing here. But you'd have to predict, in the case of the vinyl fluorine, the use phase is, pretty uninteresting. It sits there and we have to clean it, obviously. And then at the end of life, we have to pick it up and decide what to do with it. And so those would be interesting things to add to a broader analysis. But at the point at which you're making a decision, often this is enough information.
Just a related question. Actually, for the crop protection example, since you took into account how much chemical was needed for the protection, it was outside the gate in some way.
You're right. But in that case, the product was a field, a hectare of land instead of a square foot of vinyl fluorine. So yeah, but you're right. And that's a good observation. I think that in the best of all worlds, if we wanted to focus on specific products and chemical substitution, we could carry the analysis all the way through to cradle to end of life. But at this point in time, getting the information to designers about which chemical has which impact in the supply chain. And usually the supply chain turns out to be a very dominant part of the overall impact. And so, except for some applications, for example, anything that you put on a car, an airplane, that's lighter in weight, its use phase dominates the equation. It makes the amount of fuel used to go from A to B a lot less. And so there the use phase is very significant. And so we need to kind of recognize what cases we're trying to look at.
Okay, so thank you very much. Are there any more questions? Then we thank you again for an excellent presentation. We have learned quite a lot. And I hope you will also allow us to share your presentation file. If you give it to us as a PDF, we will let the participants download it if they need it.
Okay.